So last time we were looking at a fast Fourier transform, and we know from this equation, from this equation, we are working at a direct Fourier transform. Now we know we got this core part. What is Wn? Wn to the power nk. Right? So if you compare with the direct Fourier transform, in this sense, okay. So this is Wn to the power nk. Therefore, Wn, this is e to the negative j2 pi over n. Okay, right. So we have this. This it has nothing to do with little n, little k. So it is a fixed. Once it's n point dft, whether n is 8 or n is 128, but once n is fixed, I have this is fixed. Right? So we come from this equation. So we come from this equation, and then we discuss about some of the properties of this W. We divide this into two parts: even signal, odd signal, even signal, odd signal, and come to that. We find out this is also a Fourier transform equation. This is also a Fourier transform equation. The only difference is now I can change that. Well, this is on the next page. We know this is equal to n over 2. So it's n over 2 point dft. Same thing here. This is W n over 2. And then we can continue this process and divide into even part, odd part of signals. So that's what we did. That's the basic idea of all these equations. And eventually we have this butterfly plot. So we divide this n point dft into two parts. These are all the even counted signals. These are all odd counted signals, and go through n over 2 point dft. And then the result will be combined. Following the previous equation, we just combined. We got this output G, this output H, so we combine it with a weight. Weight is something is right here. This is a weight. Continue this process. We know we can also reorder these inputs and putting the n over 2 point dft to 2n over 4 point dft, this, and that. And then lastly, we can also continue with this process. And so we don't have a DFT, we don't have a Fourier transform block. Everything is very simple. It's a multiplication by a weight and then add it together. Right? So we got this, and which is a butterfly plot that we have. We call this butterfly plot of fast Fourier transform. Last time we also talked about the last step is that, well, because of some properties of W sub n, we always looking at W sub n. It's also symmetric according to the middle point n over 2. So we can continue to reduce complexity. Now here we have two weights. You need to multiply on this branch and on this branch. But because those two are the difference is just a negative sign. So we can put one of the weight here and putting here, and then putting negative 1 here. So negative 1 is very easy. You just flip that. So we need to multiply weight only on one branch, and the other branch, I don't have any weights. So it reduced the complexity again by half of the multiplication. Combine all this together. This is the final plot that we have for a FFT. Now we mentioned that for FFT, when we dealing with all these calculations here, the complexity is a complexity at the order of n. All the complexity in here is the complexity of capital N. And in my case, n is equal to 8, right? I have 8 signal, n equal to 8. Now, for all these complexity, therefore, I adding them together, I have a 3 times the complexity of that. Where does this 3 come from? Well, that's log base 2 of n, where n is 8 times O n. So the complexity is the complexity corresponding to n, actually we just write it as n times log base 2 of n. So that is the complexity of FFT. It's reduced down from n squared, that's my original discrete Fourier transform DFT, to n times log base 2 n FFT. So we reduce the complexity in a great deal if n is quite large. So the last problem that we have, we got this very simple. We don't have too much computation. The last problem we have to implement this is how are you going to reorder those input signals, right? Originally, that's 0, 1, 2, 3, 4, 5, 6, 7, 8. Now the order is 0, 4, 2, 6, 1, 5, 3, 7. And it goes through my butterfly plot. Is there any particular pattern of this input order? 0, 4, 2, 6. So I need to reorder it. Reorder. According to what? That if you program some code, how are you going to reorder that? So if we're looking into its a binary representation, now this is the order 0, 4, 2, 6, 1, 5, 3, 7. If you change that to a binary, well, because this is n equal to 8, so I have 8 different levels. Binary is 0, 0, 0, 4 is 1, 0, 0, 2 is 0, 1, 0, 1, 1, 0, 0, 0, 1, so on and so forth. Well, it's called the bit reverse reordering. So if you count it from the least significant bit back to the most significant bit, that will give you 0, 0, 0. I'm just counting backwards. If you're counting backwards, 0, 0, 1, 0, 1, 0, 0, 1, 1. That's exactly 1, 0, 1, 2, 3. Right? Go this order. But it's just the binary bits are reordered, kind of reversed, and then you make this back to the decimal number. You have these 0, 4, 2, 6. So indeed, we have a bit reverse ordering. And why do we have that? Well, due to how you deal with the problem, you kind of divide it from the top level, divided by odd and even. And then from the odd, you divide by odd and even again. So as I said, if you want to divide odd and even, you are looking at the least significant bit first. So let me rephrase what I said. Okay, so my expression when I do the FFT is I divided your signal into 2 groups. One is odd counted, one is even counted. So the first thing I'm looking at actually is the last bit. So these are the even counted. This is another 0. And these are the odd counted. So I group it according to the least significant bit. And then it's moving towards the most significant bit. That's exactly what we have here. So you're taking this the first. So it's a bit reverse ordering. You're looking at the least significant bit first when you do the ordering. So we get that. Now, if we have that pattern, then it will become very easy to program that. Everything will become very smooth to go through this FFT. The one we had before is called a decimation in time fast Fourier transform. Decimation in time, because I divided into even part and odd part decimation. Now we have a lot of the definition in decimation in signal processing a lot. Decimation simply meaning that I move a part of signals. We know where decimation comes from. It's from the Roman legion. If you lost a battle and come back, 1 out of 10 will be killed. It's called a decimation. So we kind of borrow this concept into the signal processing. Decimation in signal, that means I'm going to kill part of those signals. I'm going to remove even part, remove the odd part. So the previous is decimation in time, but we can also do called a decimation in frequency. Decimation in frequency, you can see here is I starting from kind of the frequency part, and then moving this into a big n over 2-point DFT, n over 2-point DFT. Then I become, and then I divided smaller and smaller, right? So it's kind of moving from the frequency part, and it's really we remove some signals in frequency, So the frequency originally is even and odd content and even odd content. So it will be reordered. So the frequency index is a bit reverse index 0, 4, 2, 6, 1, 5, 3, 7. But the time domain is this regular order from 0 to 7. We also have this plot, it's a butterfly plot, that we have the decimation in frequency. Of course, the last thing people want to do is, what if I don't need to reorder time, neither do I need to reorder frequency? Sure, we can do that. The order is still 0, 1, 2 to x7 in the frequency domain. Now, at this time, what you need to do is you need to kind of reorder those connections. You can think of this topology change. You just changing these 4 to here to here, and then somehow the interconnections will kind of messed up. It's not a messed up. It's still a very nice picture. It looks like a good pattern, but it's just another way of reordering. So that's another way of people programming the FT.